Hello everyone, this is Guanghan Zhao from Tohoku University. Today I'm here to present our work, BlanchTouch, bringing fingertip blanch detection into mixed reality for touch input on flat surfaces. First, about our research background. We noticed that fingertips blanch when pressed, caused by blood temporarily leave the capillaries. This is common in healthy individuals across diverse ages, genders, and skin tones. It is visible enough to be detected by RGB cameras, and it indicates whether a firm touch is occurring. Also, previous works have noted this. However, their setups are all stationary and allocentric. We are thinking about bringing this phenomenon to a practical context to see if we can leverage this phenomenon and use it as a trigger of touch input for MR devices. Here is our prototype of BlanchTouch. As we can see from the video, it can handle different types of interaction in MR. As the first step of developing BlanchTouch, we use an external camera, which is because the HMDs that we are using blocks the access to the built-in front cameras. And we get the real-time finger tracking with MediaPipe model to extract a fingertip ROI, and we pre-processing these images streamed to the algorithm with Gaussian blur to suppress the noise and sharpening to enhance feature definition. Next is about our CNN model. The architecture of this model is like this. It was based on the ResNet 50 architecture with depth-wise separable convolution applied. This design is simple but lightweight and effective, fits the task of input in MR very well. Regarding the dataset that we use for our CNN model training, we recruited 16 participants with diverse skin tones and collected 70,000 images to train the model. As a result from the test set, we got a high accuracy and a low loss. The next step is to develop an interactive subsystem. It was aimed to ensure easy but robust interactions in those walk-up and use contexts. We allow users to play UIs on real flat surfaces while pinch and drag, and then interact with those UIs by touch freely. We utilized a raycast selection method instead of just simply using fingertip banded colliders. This works even with imperfect UI surface alignment, and there is no calibration needed. Also, for the raycasting, we included a lag compensated mechanism to improve the accuracy during the fast typing. And this 39 millisecond is based on our pipeline's delay. As we can see from the video, the ray is not targeting the user's real-time fingertip, but the delayed position of the fingertip in case that there will be some misinput because of the delay from the pipeline. Moreover, we included an anti-jitter function that enforces 200 milliseconds minimum interval and require consecutive release signals between touches to mitigate the chance of having jitter caused misinput. Then we conducted our experiment 1, the system evaluation experiment. We recruited 24 participants, and the task was to touch on the crosshair, as we can see from this video. There are 3 different surfaces applied: white wall, wood, and concrete. These 3 are selected because of the daily usage on such surfaces. The results we collected from the system evaluation show that the system performed the least false negatives on the concrete surface, and the system is robust to false positives. The overall classification performance is very high, and the touch offset showed no significant surface effect with a global mean area of 5.33 millimeters. And also, a 19.75 millimeter diameter button would capture 95% of touches. Regarding latency, we found that our pipeline latency is approximately 39 milliseconds. However, the motion to photon delay is 297 milliseconds. This is kind of slow, but considering the low spec devices that we were using in our implementation, it is understandable, and it can be improved by using those high spec devices like high refresh rate cameras. Next is our experiment 2. It's a comparative study. We recruit the same people in the experiment 1, and the task was digit input. We compare these 3 different methods. The results we got from experiment 2, the comparative study, show that the baseline method is significantly faster than XR-based method, and our method performed similar input speed as mid-air method. So it is expected, since the baseline method, the touchscreen, it is always very fast. But our method is like in a similar speed of mid-air method. And there is no significant difference in error count across conditions. They are all same accurate. And mid-air caused highest arm fatigue, while our method caused the highest finger fatigue. This can be considered as a trade-off. Lastly, participants rated mid-air poke method for its feedback as the least supportive, which means participants still prefer some method that can deliver some haptics feedback to their fingers. So that's all of my presentation. Thank you for listening.